I'm glad to be here and present our recent work with Agostino Caponi from Columbia University. So the title is Systemic Risk-Driven Portfolio Selection, and the research started as a joint collaboration between Global Risk Institute and Columbia University. And now we're in the final stages of this research. So a short introduction. So mean variance analysis of Markowitz 1952. So being a graduate student at the University of Chicago, Harry Markowitz proposes an approach to select financial securities in a portfolio. So he looks at the expected returns of n risk assets and covariance matrix of returns. The portfolio represents a vector where each component is the proportion of portfolio wealth invested in the ith asset. For example, if we have only 3 assets, the potential portfolio could be 30%, 20%, and 50%. So, which means that you would invest 30% in asset 1, you would invest 20% of your wealth in asset 2, and 50%, the remaining wealth, into asset 3. So, the sum of portfolio weights must be equal to 1. Of course, based on all these parameters, we can evaluate the expected portfolio return and the variance of portfolio returns. And he formulated the problem as minimizing the variance of the portfolio subject to a specific constraint on the expected return. So we set the portfolio return to say equal to say 10%, and then among all possible portfolios that deliver these returns, we choose the one that has the smallest variance. The variance here means risk. So this was his proxy for risk. The model has been extended and modified in a variety of ways. Capital asset pricing model stems from Markowitz formulation. Arbitrage pricing theory, including Fama-French factor models, they all stem from, again, Markowitz formulation. And another possible extension would be to choose a different risk measure. So in particular, asymmetric risk, where we use risk measures such as value at risk instead of variance. The main rationale is that when we talk about variance, we take into account both upside and downside of our investments. So, but why should I minimize the chances of my returns being positive? What I want to minimize is I want to minimize the downside of my investment, so negative returns, and I want to protect my investments against those scenarios. And the value at risk can be seen in simple terms. We have portfolio losses, distribution of portfolio losses, and VaR is defined as a quantile in a sense that I can be 95% sure that my losses will not exceed VaR. The formulation of the portfolio optimization problem can now be seen in this form. I see some red. Do you see those red?
Yeah, there are these little red marks that it might be, you might have your tablet turned on so that you're marking the screen.
No, it's not actually me. That's the issue, and I cannot erase them. I can do marking like right now. That's me, and I can erase them. But these ones, no. Someone else. Oh.
Okay, well, let's see. Hopefully it doesn't turn up again.
Yes.
I'll check security settings.
Sure. So this is the formulation. So, and this is the way that we're going to proceed. We will change the risk measure in our work. So systemic risk. So the global financial crisis of 2007-2008 and the most recent COVID-19 pandemic highlighted the importance of accounting for systemic events. And systemic events are extreme form of risks that can have severe consequences on the financial market. In our work, as opposed to, say, Markowitz and VaR formulation, we introduced additional variable, market index. So we have a portfolio return, RP. We have market index, return on market index, RM, expected market return, and standard deviation of the market return. So, and in what follows, we will always work with the joint distribution of the market and the portfolio returns. One standing assumption that we are making here is that the joint distribution of the n assets returns and market returns is multivariate students t distribution. The degrees of freedom is greater than 2, strictly greater than 2. That's the assumption that we'll make. The assumption makes sense because, again, we're talking about systemic risk, and we want to take into account the fact that typically financial returns have heavy tail distribution. And student t distribution allows to model this. In particular, when degrees of freedom are small, we have heavy tails. When degrees of freedom increase, the tails become thinner and the distribution converges to the normal distribution as number of degrees of freedom goes to infinity. And in particular, when degrees of freedom is equal to 30 or 100, well, the student t distribution and normal distribution become indistinguishable. So first we define the market VaR. So RM is the return on the market, so minus RM are the losses on the market portfolio, and we define QM as the confidence level of market returns. So in particular, the probability that market losses will not exceed VaR is equal to QM. So QM 0.95, 0.1, 0.90, so pretty much we want QM to be large. So, and we also define the CoVaR, conditional VaR of the portfolio, as the value CoVaR satisfying this equation that you see on your screens. So it's basically the VaR that we can see above, but we now take into work with conditional distributions. We condition on the VaR fact that market is stressed. So the return on the market is equal to minus VaR, or the losses of the market portfolio is equal to VaR. So we define these two quantities, VaR for the market and CoVaR for the portfolio. And visually, if we look at the joint distribution of portfolio return and market return, what we're interested in is this small strip when the market return is fixed at minus VaR and portfolio returns cannot exceed minus CoVaR. It's not the only formulation that we will consider, and we call this formulation market is at its VaR level, meaning that the return on the market is equal to minus VaR. So the performance criterion of the investor is the co-expected shortfall. So we condition here, we find the expected losses on the portfolio in a low portfolio, conditioned on the low portfolio returns and stressed market conditions. So we want to consider those rainy days and want to find the portfolio that performs reasonably well. So here is the formulation of the portfolio problem. So we minimize co-expected shortfall subject to standard set of constraints. So portfolio return is fixed at some number UP and weight sum up to 1. So the first step is, of course, to derive the expression for the objective function that we're trying to minimize. So the objective function consists of 3 components. It's the portfolio expected return, it's the portfolio system covariance, covariance of the portfolio with the market, and the portfolio variance. So the first and third component are similar to the Markowitz formulation. QM and QP are the confidence levels used in the definition of VaR and CoVaR respectively, and sigma is the column vector of covariances of each risky asset with the market. So some observations. So first, a large value of confidence level for the market portfolio implies a large weight given to the covariance. So this weight is large when QM increases. So what is the intuition for this result? So when QM is large, it means that we're considering more adverse market losses, market scenarios. And by construction, we already conditioned on the market being in stress. So in simple terms, if we have a high correlation with the stressed market, it's bad. So we better put a larger weight in our objective function on the portfolio system covariance in this case, because we consider very negative, very adverse scenarios of the market. So the third term has this weight. So if QP is large, so if the confidence level for the portfolio returns, the investor assigns a large weight to the portfolio variance. By construction, again, the losses on the portfolio are bounded from below, but they're not bounded from above. So losses can be as high as possible, but they cannot drop below CoVaR. And in this case, when we increase QP, the variance becomes particularly dangerous for the portfolio, because increase in variance implies very high potential losses for the portfolio, with still bounded the downside. So this is like the way that we confirm that the objective function makes sense. And then we find the portfolio that minimizes the objective function subject to the constraints that we find. At this point, nothing is new. So we use the results from previous literature to optimize, to find the optimal portfolio. And we will use the insights that we just described when we get to a different new formulation, more realistic formulation for the portfolio optimization problem. And we will also use this result that we get in proposition 2. So the second formulation, the other formulation that we consider, is the market is at least at its VaR level. So the only difference from the previous formulation is that instead of considering the market being at the VaR level, we consider that losses can actually exceed VaR level. So, and graphically, we no longer have a strip on the joint distribution, but we have a segment of return distributions that we are focusing on. So again, market return can be below minus VaR, and portfolio returns are below their CoVaR level. And we still have two parameters, QM and QP, which are confidence levels for the market portfolio and for the portfolio of securities that we consider. In simple terms, we want to account for losses below VaR, more extreme scenarios of market returns. The co-expected shortfall is defined similarly, and again, the only difference is this sign. So before it was equality, now we allow for losses going below VaR. Losses going above VaR. So portfolio selection problem is formulated similarly. So we minimize the co-expected shortfall for this new formulation, subject to standard set of constraints. So again, the first step is to obtain the analytic expression for the objective function, and we were able to derive it in this rather simple form. So this is portfolio return, expected return. This is portfolio standard deviation, and we have this additional coefficient here, which is a function of rho, correlation of the market with the portfolio, multiplying the standard deviation of the portfolio. So it can also be shown that this coefficient lambda increases with respect to correlation. So the higher the correlation of the market with the system, the larger the value of lambda. The function lambda bar can be regarded as the weight that the investor assigns to the portfolio standard deviation. So how does this result make sense? So the derivative of lambda bar with respect to rho is positive, and it multiplies sigma standard deviation of the portfolio. So intuitively, when the correlation with the market is higher, it increases. The portfolio standard deviation becomes very important to take into account, because again, by construction, our losses are bounded from below. but they are unbounded from above. So being correlated with the stress system is very dangerous for an investor, and that's why more emphasis should be paid to the portfolio standard deviation. Notice the similarity to the Markowitz formulation when this lambda is pretty much just a risk aversion. In our case, it's this risk aversion depends on the correlation with the system, with the market. Unfortunately, there is no way we're able to do some analytic results as far as the dependence of the objective function on the confidence levels is concerned. So we did it numerically, and the typical result is shown on the screen. So we have a figure here, so level contour lines of the objective function for different confidence levels. So confidence levels are at the top of each figure. So first result is that as confidence level for the portfolio increases, the investor becomes less sensitive to the correlation of the portfolio with the market. So in the to see this, we just can go from figure B to figure A. So this is where QP goes from 50 to 90%. In this case, the curves become flatter. So these curves are steeper, these curves are flatter. So which means that they do not change much with the correlation. Why is that? Again, the same intuition carries on in here, in the sense that losses are bounded from below. So QP controls the weight that we assign to the portfolio standard deviation. So as QP increases, we are more focused on portfolio standard deviation, and of course, correlation with the system gets smaller emphasis, smaller focus from the investor. As the standard deviation gets higher, the objective function becomes more sensitive to the correlation of the portfolio with the market. So this can clearly be seen again from both plots. So for larger values of standard deviation, we see steeper curves than for smaller values of the standard deviation. It also makes intuitive sense using the same explanation. Again, when the variance increases, correlation becomes particularly dangerous because the system is stressed. So we want the correlation to be small or close to zero. And the last observation is that the level curves become flatter when the number of degrees of freedom decreases. So degrees of freedom equal 3 means heavy tails. Degrees of freedom 30 means thinner tails. So when the degrees of freedom increase, we see steeper curves, which means the standard deviation plays a bigger role in the portfolio selection. In this sense, qualitatively, the increase in confidence level for the portfolio is similar to the decrease in the number of degrees of freedom, qualitatively. Again, for the same reason that for heavy tails, probability of large deviation is higher. This is bad, and of course the investor wants to avoid it. So by reducing the standard deviation of the portfolio returns. Unfortunately, there is no closed form expression for the vector of portfolio weights, which minimizes the criterion that we described in the second formulation. So we must find some ways to obtain this, develop a procedure to still find the weights for the portfolio returns, and hopefully in closed form, an analytic expression, so that we can analyze them and see, get some insights into the portfolios that are optimal from the systemic risk point of view. So what we do is that we apply the first order Taylor series expansion for the lambda function that multiplies the standard deviation in the objective function around arbitrary rho zero, or is the correlation. And when we do that, we obtain the approximate value for the objective function, which looks very similar to the very first formulation when we conditioned on the event when market was at the VaR level. In the sense that we still have expected portfolio return, we still have portfolio correlation with the market or with the financial system in this case, and the portfolio standard deviation. All these terms are constants and do not depend on the portfolio rates. Based on this approximation, we formulate what we call an approximate formulation, so P2 tilde, where we minimize the co-expected shortfall, which now depends on our choice of ρ0 used in the Taylor series approximation, and third set of constraints. At this point, of course, you might wonder what's the connection. So it's a different problem. Yes, that's true, it's a different problem, but let's continue. So we solve this problem. We know that we can solve it because it's very similar to the first formulation when we conditioned on the VaR on the market returns being at their VaR level. So now we make it explicit that the optimal portfolio depends on the correlation that we chose when we used the Taylor series expansion. The solution of the approximation can actually be used to find a candidate for a solution to the original problem. So, and here we have this proposition, which is the most important proposition. So let's assume that we actually know the correlation of the optimal portfolio with the market. So this is the condition. So the correlation of the optimal portfolio with the market is indeed ρ0, the same ρ0 that was used in the Taylor series expansion. Let's assume this condition holds. Then the vector W star of ρ0 satisfies the first order conditions for the original problem. So the question is again, so what do we do? But when looking at this formula, we recognize that this is a fixed point equation. So since we know W star of ρ0 in analytic form, it's very easy to apply this equation and to find ρ0 that solves this equation. And this is, of course, what we are going to do when we solve the portfolio. It's, in a sense, also tells us that the portfolio has the same form as we developed before. In particular, once we found the value of ρ0, then the optimal portfolio has this form, and it consists of two components. The first component we can recognize as the mean variance portfolio that was again obtained by Merton in the 1970s. And the second component is the systemic risk adjustment to the mean variance portfolio. So if we look at this portfolio more closely at the systemic risk adjustment, we find that the portfolio in general has this allocation. So it alters the mean variance portfolio in a sense that it assigns, it makes the portfolio more concentrated on the stocks which have smaller correlation with the system. That's the goal of this adjustment on an intuitive level. Next, we perform the empirical analysis. So what we do is that we choose the constituents of the S&P 500 financial index for the US market and of the S&P TSX capped financial index for the Canadian market. The interval that we have in our sample is from January 4th, 2000 till August 7th, 2020. So almost 20 years of data. This yields a total of 51 US and 18 Canadian firms. We define the systemic event as a severe market decline captured by a significant drop, 40% over 6 months, of the broad market index. And as a proxy for the market index, we use the MSCI World Index. The portfolio performance is measured by risk-adjusted returns, and in this case, conditional risk-adjusted returns. So what we do is that we divide the expected portfolio returns over the standard deviation of portfolio returns, and we consider those fractions only when the market index falls below a certain threshold, C. The formula for the expected return and for the standard deviation are rather standard in the literature. So where T is the number of periods that the portfolio is rebalanced. So, and we will also consider different rebalancing frequencies. So what we do is that we construct the portfolio in January 2006. So we use 6 years of data for estimation. Then we rebalance it at a given frequency, weekly or monthly, until August 2020. For weekly rebalancing, we have 767 rebalancing periods, and for monthly rebalancing, we have 175 rebalancing periods. Although, yes, we talk about systemic risk, but we also consider the scenarios when returns are only negative. So this is just to make the analysis richer, to enrich the analysis of the paper. In particular, we consider the thresholds that are equal to 0. So whenever the return is negative, we take this, the portfolio return, record it, and then use it later to assess the performance. And since we focus on systemic risk, we evaluate these values of the thresholds, which is equivalent to 40% decline of the market index over the 6-month period. Again, for weekly returns, it's 1.5%, and for monthly returns, it's 6.7%. So we evaluate the risk-adjusted expected return portfolio returns out of sample. And for comparison purposes, we use 2 benchmarks. First benchmark is rather natural because it appears in our optimal portfolio. So it's the mean variance portfolio that we will compare it with. And the equally weighted for 1/n portfolio, which was also shown in the literature to perform quite well. Annual expected unconditional portfolio returns were set to 10%, and the degrees of freedom were set to 4.3%. So this comes from the data that we use. It shows that indeed the returns on the assets have heavy tails. So here are the results. So what you see here is the risk-adjusted portfolio returns when we have weekly rebalanced portfolios and count only the cases when the market return is negative. So we should focus on these numbers. So this is the performance of our portfolio. As we can see from each column, for example, compare these numbers, we see that our losses are smaller. So the returns are higher for our portfolio, and this is also true for all cases, for US stocks and for Canadian stocks, regardless of the values or the confidence levels. We should also notice now empirically, we have the observed fact that the standard deviation that we have here in brackets decreases as QP increases. Again, QP is the weight you assign to the portfolio standard deviation. So whenever the confidence level of the portfolio increases, with more emphasis, more weight on the portfolio standard deviation. And of course, then it goes down. It decreases. And the same is true for the QM parameter, which is the confidence level for the market portfolio. When it increases, well, the returns typically go larger and the standard deviation increases. So next, if this table is for weekly rebalanced portfolios, now we consider monthly rebalanced portfolios. So we see pretty much the similar situation. Again, the winner is the formulation that we have. So CoS, co-standard shortfall for the second formulation. And all the results that we discussed for the previous table, table 1, carry on to this table as well. Next, what we will do is that we change this assumption. So instead of conditioning on market returns being negative, we consider more adverse market returns, which correspond to the market drop over more than 40% over the next 6 months. So the situation is exactly the same. So we have a weekly rebalancing, more adverse market conditions. And the winner is again our portfolio that we obtain. So it's this formulation. The next table and the last table will show the results for monthly rebalance portfolios. Here we see a bit of a difference. So which first was kind of discouraging. For the US stocks, yes, we still see our portfolio to be the winner, has smaller losses, larger returns, and for the US stocks, it even generated positive returns. But this is not the case for the Canadian stocks. However, when we looked at why it happened, at the results, we realized that we had only 4 observations that were available once we filter only the returns that satisfy this condition. So of course, 4 observations is not sufficient to make any conclusions, and we attribute this behavior to exactly this case when for Canadian stocks, if we condition on these adverse returns, we get only 4 points in our sample. So that's why these results are kind of unreliable. We also investigate the level of diversification of optimal portfolios and its dependence on the confidence levels, QM and QP. So to this end, we use the sum of squared portfolio weights to measure diversification. The sum of squared portfolio weights at a certain level is given as the sum of squared portfolio weights. And it means that a lower value of this index reflects a higher level of diversification. So here are the results. We report the results only for the US market, because for Canadian market and for the US market at different frequencies, the results are very similar to this picture. So a couple of observations. So first of all, our portfolio, where inequality that we developed in this paper, is always less diversified. So it's the top line here. It becomes less diversified if we increase the level of confidence level for the market portfolio. So why? Because again, if we go from this figure to this figure, we see that increase in QM gives us a lower level of diversification, because increase in QM implies more emphasis is paid to the portfolio system covariance. So this is an expected result. And for the case of increase in QP, if we can compare these plots, so AC with B, if we compare, so it means that with the confidence levels are fixed and confidence level for the portfolio are increasing. If we compare them, then we see that the diversification is actually increases. Why that happens? Again, confidence level for the portfolio controls the weight that we assign to the portfolio standard deviation, which means that as QP increases, the confidence level increases, we should be closer to the Markowitz formulation. The Markowitz formulation is a trade-off between expected returns and standard deviations. So this is also results that we pretty much expect. So that's it. Thank you very much for your attention.
Okay, great. Thanks, Alexey. That was definitely within time. So we have lots of time for questions and informal discussions afterwards if people have. So please remind you to put in your questions into the chat. I don't see any at the moment. We can give everyone some time to formulate their thoughts and put in questions. But maybe in the meantime, I can ask a couple that came to me while you're giving the talk. So one question I had is how much of the results are really contingent on this particular multivariate student T model that you assume that the market and the portfolio and the underlying assets follow?
Mm-hmm. Yes, we explored the case when we had degrees of freedom equal to 30, which means we're in the normal world.
Mm-hmm.
The result did not change at all. So we also did some robustness checks for other values of the degrees of freedom parameter.
Mm-hmm.
No change. So we still have our formulation, the portfolio co-explainer shortfall, as the winner in this case. So results remain the same.
Right. No, I was more thinking about so you have a particular mathematical result for the CoVaR equals, right? When you and then for the CoVaR less than or equal to, you have to use some numerical techniques there. But for the equals case, you have an explicit formulation for the portfolio weights, and it seems as if it depended. It seems to me that it may depend on the particular multivariate student T model, or does it also have a similar form for any elliptical class of distributions for returns?
Yes, here, Sebastian, yes, we did not check this. I would expect, of course, that form might change, but intuitively, what we should focus on is, of course, expected returns, standard deviation, and the portfolio market covariance. However, for some other distributions beyond the elliptical family of distributions, yes, we could get some different forms of the objective function, but we didn't check this.
Okay, all right, fair enough. Yeah, I mean, it's already challenging in and of itself. So I now see some questions coming through the chat. So Felix Wong, would you like to unmute yourself and turn on your video to ask your question? If not, I can read the question. So the question says, I'm not a math person. Can you try to explain how to diversify in layman's term in order to have a better returns result? Okay, that's probably a fairly generic question, but maybe you can take a stab at it there.
Yes,
Alexey?
yes, yes. So have a better returns result. So again, Markowitz focuses on portfolios that are mean variance efficient. Here we have one more parameter, which is a correlation with the system. So in layman terms, if you want to get good results, you not only consider risk as a standard deviation and returns, you also try to find a good balance between three variables now, which is the correlation with the benchmark, with the system, expected returns, and standard deviation. Of course, constructing this like in your head, it's difficult, but it's impossible, I would say. But the portfolio that you want to construct based on our formulation will be the balance between these three terms. So if it's like in layman terms, how would I describe it? But of course, math should come here because it's like the balance between these three variables. When you have the correlation structure among the variables, is not easy to do. But in layman terms, this is how I would describe this.
It's kind of like a three-fund theorem, effectively, right?
Yes, and we actually also prove this fund theorem that actually in the Markowitz, there are two portfolios that you need to generate all portfolios on the frontier. In our case, three portfolios are needed to generate all portfolios in efficient frontier in our case. But in our case, it's surface, not just a curve.
Okay, next, I think Stan has some questions or comments here. So would you, Stan, I see you turn on your video already. You can unmute yourself and ask. Maybe I can unmute it for you. How do I do that? No, I can just say ask to unmute. You might be able, you may have been prevented from unmuting before, but now, there you go.
Okay.
Yeah, I
All
just.
right. So Alexey, very nice work. To make it more practical, I want to check if you have some simple constraints, like constraints on positions, like say maximum 3% or something like that, which are typically imposed, I mean, per position. So do you have something like that, or most probably it would be very difficult to do analytically anything with that?
Yes, thank you for the question, Stan. No, we didn't consider it. Of course, it's realistic. First of all, typically in realistic scenarios, we preclude short selling. So all weights should be positive. But this is not a binding constraint, but the one that you mentioned, maximum 3% per stock. Yes, this is realistic, and this is what pretty much they do in the industry. They do have bound, but we did not consider it, and I'm pretty sure it will not yield analytic solutions. We will have to solve it numerically, which I think should not be very much problematic, but we did not consider this in the report.
Yeah, because when you have done simulation numerically, you are supposed probably to impose such type of constraints. Otherwise, what you do is out of sample, whatever comparison, it may be just loaded to few assets, and it's very unrealistic.
Yes, that's a common pitfall of Markowitz optimization. We have lots of stocks. It tends to concentrate on just a small subset of those stocks. But yes, it was something that we did not consider at this point, and like the optimization, it was quite challenging to prove that proposition 5 already to solve it in the current form. But for your case, I'm pretty sure we must adopt some numerical approaches to do this, for sure.
Also have provided couple of references which don't have so nice analytical results, but it's just factor analysis when you identify these factors that market is in trouble or company is in trouble, and depending upon that, you would estimate systematic risk, and in this case, VaR is used and drawdown is used. So probably it may be of interest for you to see what is going on with a bit different approach to a similar problem. Okay.
For sure. Thank you very much, Stan. Thank you. I will definitely look at those papers.
Great. Cameroon Wisentowicz, I hope I didn't butcher the name too much. If you'd like to unmute yourself and turn on your camera, you can ask your question.
All right, here we go. Hi, Alexey. So my question is, I'm trying to understand your result in a little simpler way. And are you saying that when you create this optimal portfolio by looking at the downside tail, are you saying that if it's weakly correlated with the market, for example, the S&P 500, and if you look at that sub-portfolio, and in that sub-portfolio, the correlation amongst its constituents are weak as well, like zero essentially, that it performs best when the market is drawing down or having big negative returns? Is that what your result is saying?
Yes, that's true partially, but here the picture is not so black and white. So sometimes, probably because of the specific correlation structure among the assets, we might go for a large negative correlation and invest in that asset.
I see.
Yeah, so, but sometimes, yes, typically most of the time you invest in assets that have smaller correlation with the market, because again, we condition on the fact that market is stressed already. So I better be kind of not independent, but uncorrelated definitely from that part.
And if I could just a follow-up question, like if you just look at the performance of this downside protected portfolio, if I could call it that, how does it perform like when the market is just say performing irregularly and not drawing down? Does it perform comparably or worse? Or so I guess the other way of phrasing it is this just like saying, you know, I want to have a portfolio where I just don't want to lose anything. I'm just protecting my downside and then letting it run.
Yes, The question is like we consider like stress time, but what about normal times? So does it perform well, or if it doesn't perform well, so how bad does it performs? So when we compared it, the results are not here, not in our working paper, but it performs sometimes weaker, sometimes better, but there is nothing like clear cut. We cannot say like in this case it always performs better in crisis, and for this reason we couldn't come up with like good explanation for why we see this behavior. However, by construction, the portfolio returns are fixed, so we have the same constraint. Portfolio returns are equal to, let's say, 10% per annum. So it's only the objective that changes. So yeah.
So just sorry, I don't want to hog everything, but it just tweaked another question. So does that mean your portfolio construction would be amenable to higher leverage? So like borrowing more money to invest in that portfolio?
Yes, that's another thing that we did not look at, because again, we don't impose any constraints on short selling. So, but when I looked at the returns, so not at the returns, at the portfolio weights, I did not see like -10 or 10. So those are a little crazy numbers that you might typically see in the Markowitz formulation. So it was rare cases we see like 2, -2, something close to -2, but most of the time they were about from -1/2 to 1/2, something like this. But again, it depends on the result, or not on the result, it depends on the expected portfolio returns that we specify. If we have like 20 portfolio returns, then of course we'll have much more leveraged portfolios.
Right. All right, thank you. Very interesting work. Thank you for presenting it.
Thank you, Cameron. Thank you.
Okay, next we have Tom. Tom, would you like to unmute, turn on your camera and ask your question? Great.
Here I am. Very nice talk, Alexey. Could I just ask a little bit about the degrees of freedom in your numerical experiment? So presumably you estimate using the market data. What kind of estimator actually works for these markets in these times? For
maximum likelihood. But I want to caution here, we were not doing any state-of-the-art empirical models here, like GARCH, to estimate variances. So that's why we decided to focus more on the calibration, not the calibration, estimation, but we estimated using like old-fashioned ways, like maximum likelihood estimator.
Right. Okay. So, but I wasn't quite clear. Maybe you said it, but I didn't hear it. What degrees of freedom did you actually use in your optimal weight formula for those experiments?
4.3. 4.3.
Oh, okay, 4.3. And that's sort of what you're kind of guessing the maximum likelihood parameter is.
Yes.
For this data.
Yes. Yes.
Okay. Okay. And then I think you said when you. Right. And then if you put in B equals 30, that's pretty close to the sort of the normal, the standard mean variance portfolio, is it?
Yes, it's exactly. So we considered in our robustness checks 3 values, so 5, 10, and 30.
Yeah.
So and in all these cases, we got the same results. And 30, yes, as you said, exactly, we are pretty much in the normal distribution world.